it's actually quicker to do it by hand than it is to even type it into the calculator, right? Once you get a handle on these concepts. So you recognize number 3 as a difference of perfect squares because it's a difference of perfect squares. All right, not being a wise guy, there's a minus sign and there's 2 perfect squares. All right, x squared, anything that's raised to an even power, any variable that's raised to an even power is a perfect square, and 49 is a perfect square. If you're not sure, chuck it into a calculator, take a look. All right, the way we factor those is 2 sets of parentheses. We take the square root of the first term and the square root of the second term. And as long as we remember to alternate the signs, one positive, one negative, doesn't matter what order, then we'll have our factors. Square root of x squared, just divide the exponent by 2. You get x. Square root of 49 is 7. Now I have my factors. Take each of those factors and set them equal to 0. Don't forget the or symbol. I'm going to be looking for that. When we take a test on this, if you don't have the or symbol in there, you're going to lose some credit. All right, not a lot, but enough that it'll be annoying. All right. So add 7 to both sides. If you want to skip this step, that's fine. I mean, save yourself a little bit of energy. You would get x is equal to 7 or x is equal to negative 7. All right. So that would be one type of problem. All right. That's the difference of perfect squares. Next up is the trinomial. Now the trinomial is the one where if you're going to have difficulty with this, once people get really, really good at factoring, the only thing that they ever really struggle with is the trinomial where the leading coefficient is something other than 1, right? Because all the different possible combinations that could come into play. That's where the calculator would come in handy. All right, so I'd look at this and say, all right, well, what are 2 numbers that'll multiply to 3x squared? So I'm thinking 3x and x. And then I'm thinking 2 numbers that are going to multiply to a 4, in this case negative 4. So that's 2 and 2 or 4 and 1. All right, so I wouldn't, for example, want to put the 4 here because that's going to give me an outer product of 12. That's pretty far away from what I want it to be. All right, so I'm thinking 2 and 2. So I'll give that a look. 2x, 6x. Well, if the 6 is positive and the 2 is negative, that'll work. All right, so negative 2, positive 2. And those would be your factors. But let's say you tried every possible combination that you could think of and you just couldn't figure it out. Which usually means that you missed a possible combination along the way. All right, so it's like, I thought I accounted for everything, but then somebody comes along and says, did you try this? And you're like, oh, that's the one thing I didn't think of. Then what do you do? All right, because if you can't think of it, then how are you going to come up with the right possible combination? You probably not. All right, so we go to the calculator, type in 3x squared plus 4x minus 4. All right, as long as it's in the standard form, the general form, where everything except for 0 is on the left-hand side. So you bring everything over to the left, 0 on the right. Then you use this technique, zoom 6. If you're able to pluck the solutions right off the graph, the x-intercepts, that's great. If not, then maybe you got to zoom in a little bit. And just move my cursor over. I try to get it centered in the graph. Let's see here. That's definitely a fractional value. This one might be a whole number. I can't really tell. This looks like it's negative 1. It might be like negative 1.5. Oh, actually, it looks like it's negative 2. All right, so if I had to guess, I'd say negative 2, but I don't want to guess. So I'll do second trace 5. Second trace 5 once you have your graph. Then get as close as you can to whichever intersection you're looking for and hit enter, enter, enter. So I have one intersection, x is equal to -2. And the other one, enter, enter, enter. That one's 0.6 repeated, which, you know, hopefully you recognize as 2/3, but maybe you don't. If you don't, then you got to do that extra step. You go into the home screen, second mode. You type in the x value, brings up the decimal. And then you hit math option 1 to convert it over to fraction form. All right, so we have our answers, and what we talked about yesterday is that the denominator corresponds with the coefficient within the expression. So this 3 is going to be the coefficient over here. This 2 is going to be the constant value. So 3x and 2. All right, that -2 could be thought of as a 2 over 1. So the 1 would be the coefficient. I'm just going to use the same color scheme. And we only work with the really the absolute values. We ignore the negatives and positives. So one x and 2, then it's just a matter of the signs. Which one's going to be positive, which one's going to be negative. It's always the opposite sign of whatever you have in the root. All right, so this one would be positive, and this one would be negative. All right, so there's a lot of different rules to keep track of, but it's manageable. You just gotta. I mean, it's a matter of study. You know, you gotta familiarize yourself with these processes, right? Because the alternative is to become like a master factorer. Right? If you're really good at factoring, then you don't have to worry about any of this stuff. But if you're a little iffy on your factoring, then you need all the help you can get. You can't just disregard this approach and say, well, I'll just do it using the other method. I like the other method more. But if you can't do the other method, then it doesn't matter how much you like it. You know? So take the time to get to know whatever approach you think you could be most successful with. So x plus 2 equals 0, or 3x minus 2 equals 0. And then you'd solve each one. But we already know what the solutions are, so we're not going to bother with that. All right. The last one I wanted to go over was, it's another binomial, all right? But it's not a difference of two perfect squares. One, it's not a difference. And two, we don't have both parts being perfect squares. The first part is, second part isn't. All right. So the only alternative well, there's two possibilities. Maybe it's not factorable at all. But the other possibility is that there's a GCF. So my GCF, I notice a common x can be factored out. So x squared divided by x to the first, keep the base, subtract the exponents, gives you an x plus 6 equals 0. Set each factor equal to 0. And you get x equals 0 or x equals -6. All right. So you look at these three solutions and you see that two of them are pretty easy. One of them is a little trickier. All right. The trinomial case is the tricky case. But if you can get a handle on the difference of perfect squares in the GCF cases, that cuts the amount of work that you have to, or really the thinking that you have to do, down substantially, where you only really have to worry about the trinomials. All right, squares, that would be a problem. All right, we're looking for two perfect squares separated by a minus sign. All right, if you see that and there's no GCF, then you get right down to business, and getting down to business means opening two sets of parentheses, taking the square root of the first term, putting that, oh, I cannot write, putting that here and here, taking the square root of the second term, putting that here and here, and then just making sure the signs are different. So one gets a minus and the other gets a plus. Doesn't matter what order you do it in. Plus minus, minus plus, doesn't make a difference. All right, so the square root of x squared, when you take the square root of a variable raised to a power, you just divide the power by 2. All right, so x to the first, x to the first. The square root of 1 is 1. And so these would be our factors. All right, so take each of your factors, set them equal to 0. Solve. This part I'll let you kind of skate on. Like, you don't have to technically show the -1, -1, +1, +1, like the act of adding and subtracting. If you want to jump right to the final answer from here, that's fine. All right. So instead of showing what I'm showing here, -1, -1, +1, +1, because I'm asking you to do a fair few problems. If you wanted to skip that step and just go right from here to here, x equals -1, because you really should be able to do that in your head. I mean, for some of the more complicated ones, maybe a different story, but you know, these aren't that bad. So we have x equals -1 or x equals +1. All right. Now, you really shouldn't need a calculator for this one, but I'm gonna use it to go over the calculator process again anyway. So y equals, you hit the y equals key. You put the left side in, x squared -1. You put the right side in, which is 0. Take a look at the graph, zoom 6. If you have a nice clear view of what's going on, then you're good. Maybe you could just count the tick marks and be done with it. If you need to zoom in, zoom in. You could use the zoom box feature, but zoom in will be fine here. Gets us a pretty good look. It's pretty clear that that's at 1 and -1. So that'll give us our answers. So we're in really good shape with a question like this. All right. But if we needed to, well, let's say there weren't nice clean answers, you'd use second trace 5, go to one of the 2 intersection points, and hit enter, enter, enter. And it's just the x value that we care about. So we got the 1, we would repeat the process, second trace 5, hold down the left arrow, goes a little quicker, enter, 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 and you get your -1. All right. So that'll help you backfill the factors if you need to. We'll do partner A, number 8, in a minute, but partner B is right below this, so it kind of makes sense. So we're looking at 2 terms. Whenever we see 2 terms, we think difference of 2 perfect squares, but I don't see that. Right? I see a perfect square. I see one of them, but the other one's not a perfect square. But I do see a common x. All right? We should always be looking for a GCF in any polynomial. All right? If it's there, we need to account for that in our first step. It's just not always there, so it's easy to kind of lose sight of that. All right? In this case, we have a common x, no common numerical value, but I can factor out a GCF of x, divide each term by that x. X squared divided by x. Let's really keep the base, subtract the exponents. X to the first. X divided by x goes away. Divides to equal 1. So 5 times 1 is 5. My pen just glitched on me there for a second. So I have my 2 factors. Set each of my factors equal to 0 and solve. So x is equal to 0. Or x minus 5 is equal to 0. So like I said, you could just jump right to the answer here if you want. So we would say x is equal to 0 or x is equal to 5. And again, you could get that by looking at the picture too. All right, and the last one, the most complicated one, out of the 3 that I selected to go over, 5x squared minus 28x plus 15. If only that 28 was a 25 or a 30, then we'd have a GCF and it'd be a lot nicer, but it's not. All right, so we have to factor this trinomial. we look for values that'll multiply to 5x squared. That part's easy, because how are you going to get to a 5x squared? 5 is prime, so it's going to be 5 and 1. So 5x and 1x, or 5x and x. Then we got to think about how we're going to get to a 15. All right, different possibilities here. 1 and 15, 3 and 5. All right. But I need to get to a 28 through addition. All right. So if I put, let's say, for example, if I put the 1 and 15 here, that's not going to be helpful. All right. Because 15 times 5 is going to be way too big. I think that's 75. I think so, anyway. So that's way too far away. All right, if I go the other way around, I get closer. I get 15 and a 5. That gets me to a 20. But it's not close enough. So then the 3 and the 5. So I try the 3 here and the 5 there. I would not try, and honestly, I wouldn't even really try the 15 here, nor would I try the 5 here, because that would create a GCF in my first binomial. If there's no GCF in your original trinomial, there won't be a GCF at any point in the expression, whether it's in the original or in the factored form. All right. So the 3 would have to be here with the 5 being here. All right. So that gives me an outer product of 25, inner product of 3. So 3x, 25x. If they're both negative, that'll get me to a negative 28. So that's great. That's what we need. All right. So I use trial and error there. But let's say I went through all of my different possibilities and I just couldn't figure it out. I tried everything. I tried everything that I could think of, which means that I missed something along the way. Now, that doesn't mean you have to get it wrong. You just go to the calculator. All right, so we look at 5x squared minus 28x plus 15. As long as it's in the appropriate general form where everything's over on the left-hand side, 0 on the right, you'll have it set up perfectly for the calculator. All right, you type it in, zoom 6. All right. I don't know how clear of a picture this is. Maybe we got to zoom in a little bit, but this looks like it's probably a 5. But it probably only looks like it's a 5 because I already know the answer. All right, so I don't want to assume anything. So I'm going to do second trace 5. And I'm going to get over to this one. I want to confirm that that's a 5. I suspect it's a 5, but I want to confirm it. Let's see, right about there. Enter, enter, enter. Yeah, it's a 5. Okay. So I know that one of my roots is x equals 5. All right. So that means that the corresponding factor must have been x minus 5, because that led to x minus 5 equals 0. When you add 5 to both sides, that gives you x equals 5. That's all I need. Because now I would just think, what do I multiply the x by to get 5x squared? 5x. What do I multiply a negative 5 by to get a 15? A positive 15, a negative 3. So just by knowing one of the roots, I'm able to figure out all of the factors. So then 5x minus 3 would equal 0. This one I would show the work. So 5x would be equal to 3. And then when I divide both sides by 5, I get 3/5. All right, so x would be equal to 3/5, or x would be equal to 5. All right, so that's just using your calculator to its fullest potential. You know, maybe not fullest potential, that's an exaggeration, but yeah, it's an available, allowed resource, so why not use it to help you when you get jammed up on a problem. All right, So that would be the approach that you take. And you could also get the other answer. You can get the 3/5, second trace 5. It's just going to give it to you in decimal form, but if you're comfortable with that, you look at it and you're like, okay, 0.6, I don't know what that is in fraction form. Just type in the X in your home screen and it'll bring up the decimal. Now, it's not too hard to, it's not hard at all to write 0.6, but if it's a nasty decimal, you want the calculator to do it for you, you would just hit math followed by the frac, right? Math option 1, and it'll convert it over for you. All right, so you can get your answers there, and that'll help you backfill the factors. All right, and the relationship's really nice because if you recognize again the relationship between your answers and the factors, then that really goes a long way. So in this case, you know, it's pretty easy to see, I think. I don't think I'm making anything up here, but you know, when you look at your answer here, x equals 3/5, and compare it to the factor that it came from, it's got the same ingredients. Right? So that denominator of 5 corresponds with the coefficient. That numerator of 3 corresponds with the constant term. All right? The same thing happens with the 5 because that 5 is really a 5/1. The denominator corresponds with the coefficient. The numerator corresponds with the constant term. All right? So you could actually just pluck the values from your fractional answers and use them as coefficients, but only if you recognize those relationships. Now, I'm recognizing those relationships for you, but if you go the rest of the way, then you can use that information to help you even if you're struggling with factoring, because there's no reason why you should be getting these questions wrong just because you struggle with factoring a little bit. All right. Forward one, although none of them are straightforward really if you don't know what process to use. Right? But once you identify the correct approach, then it becomes straightforward. Right? So if you look at number 9 here and you ask yourself, because when you're dealing with a binomial, there's 2 possible things that you want to be looking for, at least at this point. You want to either be looking for a GCF or a difference of 2 perfect squares. All right? So I don't have a difference of 2 perfect squares in number 9, so that leaves GCF. All right, but number 10 right below it, I don't have a GCF, so that gives me a sense that I'm probably looking for a difference of perfect squares. So in number 9, we have a GCF of x. I can divide out that x. So if x times x minus 2, all right, then I take each of those factors and set them equal to 0. So x is equal to 0, or x minus 2 is equal to 0. In which case I would get solutions of x equals 0, or, now when you add a 2 to both sides, you don't have to show this step if you don't want to. You could do plus 2 plus 2, or you could skip that because it's pretty straightforward. X is equal to 2. All right. So, like I said, once you identify the approach, it's not bad. But if you attack this problem as if it's a trinomial or you think it's a difference of 2 perfect squares, then you run into some trouble. All right. Now, number 10, that one is a difference of 2 perfect squares. We know that because there's a minus sign. That's the difference of 2. Well, there are 2 things, each of which is a perfect square. X squared and 16, both of which are perfect squares. All right. So we can factor it with the product of binomials. All right, so the way we handle that is by taking the square root of the first term. So this x squared, we're going to find its square root, and we're going to put it in those 2 spots I just indicated. and we're going to take the square root of the 16. That's going to go here and here. So square root of x squared is x. Square root of 16 is 4. As long as the signs are different, 1 plus 1 minus, you're good to go. All right, so it doesn't matter which is which. I'll put the minus here, the plus there. I take each of my factors, set them equal to 0. X minus 4 equal to 0, or x plus 4 is equal to 0. Solve each of them. For the first one, I'm going to add 4 to both sides. That's going to give me x equals 4. For the second one, I'm going to subtract 4 from both sides. It's going to give me x equals negative 4. All right. So like I said, not too bad as long as you know what approach you're supposed to use. Right? And just taking a look at the polynomial that you're given gives you an indication of what approach to use. There's two things. All right, what are my choices? GCF or difference of perfect squares. All right. Is it entirely made up of perfect squares? No, so it's probably going to be a GCF. Or maybe it's not factorable. All right. Now, going to number 9, that's the case of a trinomial where the leading coefficient's not equal to 1. So I know it's going to be a product of binomials. The first terms are going to multiply to 3x squared. So that's going to be 3x and x. The other terms have to multiply to 8. And that's where it gets a little bit more complicated, because the possibilities are 1 and 8, 2 and 4. Which one goes where? Who knows? You know. So I mean, if you go down the trial and error route, you'll get there eventually. But if you want to go a different route, you could use the calculator. All right. So, I mean, if you look at it and say, okay, well, clearly it's 2 and 4, or clearly it's 8 and 1. Or clearly whatever, depending on what you notice, then that's fine. But if you don't notice the relationship, then you could be in a little bit of a problem or a tough spot, right? But anyway, the calculator approach. The left side goes in. As long as it's equal to 0, right? You always have to manipulate, no matter what approach you use, you always have to manipulate your equation so that the right-hand side, or actually just one side, is equal to 0, but it's preferred that it's the right-hand side. All right. The left-hand side would then go in as y1. We'd go to the graph, zoom 6. This is a little tough to see here. All the good stuff's happening around this turning point, but it's kind of hard to make out what's going on there. So I'll zoom in, zoom option 2. I'll move my right cursor so that I'll use the right arrow so that my blinking cursor is right around the middle of that whole region of interest, I guess. All right, so it's helpful in the sense that now I could get a better view of what's going on. It's not helpful in the sense that I still can't figure out what the intersections are. So then I would use second trace option 5, which is intersect. I'll try it for this point. Enter, enter, enter. So that gives me a 2. Right? So I know one of my solutions is x equals 2. The other one, second trace 5. And again, this is assuming that you couldn't figure out what the factors were. If you figure out what the factors were, that's great. But we get 1.3 repeated here. Now, if you recognize what that is in fraction form, that's wonderful. But maybe you don't. If you don't, then you got to do the extra step of going into your home screen, type x so it brings up the decimal, and then convert that to fraction form, math option 1. So that'll give you the 4/3. All right. So the bottom number of the fractional answer is the coefficient. The top number is the constant term. So that's a 4. All right, 4/3. So the 3 comes first, and the 4 in the factored form. All right, the 2, that's a little bit more straightforward, unless you want to think about it as a fraction, because that 2 could be thought of as 2 over 1, in which case you would say the 1 is the coefficient, and the 2 is the constant term. All right. So again, if you see that it's 4 and 2 immediately, that's great. If you don't, then you have this technique to fall back on. All right. The sign contained in your parentheses, in your factor form, will always be the opposite of the sign of your solution, your root, your x-intercept. They all mean the same thing. All right. So if your solution is positive, your factor is going to be negative. In both cases, they're positive, so the factor is going to be negative. All right. So you can get around factoring so basically, you can show the work for factoring without having to know how to factor, which is kind of nice if you're in a jam. All right. But it's not as you can see, it's not the most efficient way to go. All right. Because I had to do all of this stuff to come up with a solution, to then come up with the factors, to then solve those factors to come up with a solution. All right, that's a lot of behind the scenes work that needs to happen in order to avoid something that probably isn't that bad if you just have the patience to try all the different possibilities. All right, but yeah, if I take my 3x minus 4, set it equal to 0 and solve. If I take my x minus 2, set it equal to 0 and solve, I'll get these two values. It's a good backup plan to have, all right? But we want to be able to handle the factoring because it helps you avoid having to do all this stuff, right? But at least you know that you have this as an option if you need it.